Hey, this is Math 7, Unit 8, Lesson 17, more about sampling variability. In this lesson, just so you guys know, you may or may not be doing it in class today or any day. It's an optional one, and even for me today, I'm going to go through a few parts of it, but really just kind of do one activity and the summary and move on to the homework activities. And part of that's just because I don't have the resources to do it here at home, and the other part is it just takes more data to do at a classroom setting so that I can do here. So it says, first of all, comparison samples. The first thing you'll be doing, it says the other day you worked with the reaction times of 12th graders to see if they were fast enough to help out the track meet. So you gotta look back at your sample from before. That was back at lesson, I'm not quite sure, 15, 16. And then you want to calculate the mean reaction time for your sample and then see if your sample and you got the same. So back for that reaction time, I think reaction times are somewhere between like about 0.3, let's say about 0.30 was like a mean. So maybe my mean reaction time from my sample was 0.3, and maybe my partner had one that was 0.34, okay? Oftentimes, you and your partner are going to get different samples, right? They're not going to be the same. And the reason for that is because whenever you're doing a sample, you are selecting different random people from the population. Okay, when you draw or select different numbers or different samples from the population, the mean changes. Okay, so if I select 10 numbers and you select 10 different numbers, we might come up with a different mean. That's just going to be the normal thing because we're not picking the same numbers. Again, imagine if I have numbers 1 through 100 and I pick out 10 of them and you pick out 10 of them, and then we find the mean. They're going to be different because we're drawing different samples from the entire population. Okay, or even different samples from the sample itself, I should say, right? Because probably you're not going to put every number out of every kid in the school. This one we did, but that's the idea. Okay, so the more that happens over time, the more times you do the experiment and go through the process to find the mean, then the more that your samples are going to get closer to the actual population sample. And that's our goal here. I might get a 0.30, you might get 0.34, someone else might get 0.29, someone else might get a 0.32, right? And someone else might get a I don't know, 3, let's go 30 again. Well, if there's 5 people getting different means, and maybe this is what you have at your table group, if I take all of those means and I combine them, we're going to add them up here. I'm just making up numbers here, and I get that, and divide that by 5, in this case here, all that divided by 5, I get 0.31. So if I take the mean of all the means, right, then I'm going to get a mean that maybe is even closer to the true mean of the population, because that's the goal, is to find out what's the actual mean of the population. So the more samples you do, the better your mean is going to be. Okay, so let's take a look at this here. I'm going to move over to activity number 3. Yep, 3. So in activity 3, it says the other day you worked with different samples of viewers from each of 3 different television shows. Each sample included 10 viewers. Here are the mean ages for 100 different samples of viewers from each show. Meaning they didn't do this sample one time. If you recall, in our activity, we did it 2 times, and we had a total of 6 samples last time. Okay, that's what we had, right? We had sample 2 for each one. So we had 2 from each one, 2 times 3 is 6, right? Here are 100 samples for each show. So last time we just had 2. We had like 1, 2. And we're like, oh, what's the difference? It's really hard to say what the overall mean is going to be based upon 2 data points. But here, I have 100 different data points for each of the TV shows, which means I'm more likely to be able to determine what the mean of the population actually is. So the first question to ask here is, for each show, use the dot plot to estimate the population mean. And again, look at the key word here. We're trying to figure out what is the population mean for the all. Okay, so if this was the dot plot, for the trivia game show, where do you feel like the mean is? And again, we're just estimating. You don't need to add this up. That'd be a lot. For me, when I'm looking at it, I kind of see the middle is somewhere about here, so I'm not looking for the median, but maybe the mean is maybe somewhere about here, this range and there. So I might say the mean is maybe about 58 for the trivia game show. For the science experiments you can do, you know, I kind of can ignore these outlying things and look at kind of the chunk in the middle, right? And then go, well, where's about the middle of that? You know, and go, well, let's go somewhere. I could definitely say the middle is about here, but there are more over there going down, so I'm going to drift it this way a little bit. So maybe I just go with 12, right? That's kind of middle-ish. And for this one, I can kind of point that and say, well, that certainly looks like it's kind of symmetrical and ending up somewhere about here. So for science experiments, I'm going to say 12-year-olds, and for learning to read, I'll say 6-year-olds. So I put down 58, 12, and 6. Again, this is just an estimate. So the next question then is, well, for each show, are most of the sample means within 1 year of your estimated population mean? Well, let's see. For me, on the first one, I said 58, so that would mean that when I look here, based upon that being 60, okay, then halfway is 58, 59, and this is 57. So do I have most of the samples in that range right there? For this one, not so much, okay. So not so much that one because there's a lot on the outside there, right? We forgot a lot of sample spots. So I've only included some of them if I go 1 year. So I'd say no for trivia. For this one, we started at 12. We're going to go out to 13 and then down to 11. So I see here, do I include most of the data in that box there? In this case here, we'd say yes, that one looks like it certainly. And then finally for number 6, if we're doing 6-year-olds, I go 1 year, I'm going out to 7 and down to 5, and that's going to be including everything, isn't it? Okay. So what you can see is that sample size of 100 people, or doing 100 samples, it definitely gets us closer to the actual population mean when you have more samples to look at. So for the science and the reading show, that'd be a yes. We got them all in there. So really what it means is that when you look at this population, this group of samplings here is very, very close to what the population looks like. There's still too much variance in the trivia game show for it to be accurate, but this one looks great. Okay. Now suppose you take a new random sample of 10 viewers for each of the 3 shows. Which show do you expect to have a new sample mean closest to the population mean? Alright, so if you do one, which one do you think is going to be closest to the population mean? I would say the reading one. And again, the reading one, the reason for that is, you look at the samples that we got, sample means, they're all within 1 year of our estimated population mean. So if I took another sample, it's probably going to be somewhere right around there and be super, super close. There's a chance of this one I might just get some really low numbers and be out here somewhere. Okay, and even in this one, there's a chance of being a little too high, a little too low as well. But on this reading one, they all fit within that range there. Okay, so in summary, and again, this is just a shorter version of the lesson today. In summary, this dot plot shows the weights in grams of 18 cookies. Okay, the triangle indicates the mean weight. So the mean of all this is right there. That's our average, which is 11.6. The dot plot shows the means of 20 samples of 5 cookies selected at random. Again, the triangle shows the mean for the population of cookies. Okay, so that's the mean for the population based upon all those data points there. That's the mean right there. Notice that most of the sample means are fairly close. So sample means are fairly close to the mean of the entire population. And that's what you want. You want things to be close to the population mean. This dot plot shows the mean of 20 samples of 10 cookies. So this is samples of 5, this is samples of 10. So this one has more in the samples. Well, what happens to our mean then? Okay, notice that now the dots are even closer together and they're all really tight around our actual population mean. So in general, as the sample size gets bigger, the mean sample is more likely to be closer to the mean of the population. So the larger your sample, the more your mean sample is going to match the mean of the population. And that is your ultimate goal. Okay? I'm going to pause there, let you work on your homework. I'll come back and check it together in just a few minutes. All right, 1,000, homework time, sorry, lesson 17. 1,000 baseball fans were asked how far they'd be willing to travel to watch a professional baseball game. From this population, 100 different samples of size 40 were selected. Here's a dot plot showing the mean of each sample. So think about this real quick. There were 100 samples and there were 40 people in each sample, which means if you consider this is 100 times 40, it's a sampling of about 4,000 people. Okay, again, out of the whole population. Okay, of the 1,000 baseball fans, they tried this 4,000 times. So are they asking 4,000 people? No, but they drew 4,000 names out of 1,000 possible again and again. So they're getting closer and closer. That's kind of the idea. All right. So based on the distribution of sample means, what do you think a reasonable estimate for the mean of the population? So where do you think a good mean of the population should be for this sample, distribution sample of means? So you might want to take a look and say, well, let's ignore kind of the outliers here and let's look at what's in here. Is it kind of a curve? Is it a nice curve like this? Well, if it's a nice curve like that, we would say it'd go in the middle, somewhere about here. But we seem to have some more that are higher on this end over here, so we probably want to shift it a little bit that direction, right? So I would probably shift a little bit here and maybe end up about here or so. So for me, I would estimate a reasonable estimate probably somewhere about 64, okay? And this is miles here, so 64 miles is probably a good estimate, okay? Could you do less or more? You certainly could. Could you do 62? Yes, you could. So you definitely probably want to be in this range for whatever answer you decided on. So if you pick something different than 64, stick with it. Just have an explanation for why you think it's okay. There's no right or wrong there, but you probably should be in that range. Last night, everyone at the school music concert wrote their age on a slip of paper and placed it in a box. Today, each of the students in a math class selected a random sample of size 10 from the box of papers. Here's a dot plot showing their sample means rounded to the nearest year. Okay, so we have 31 up to 42. Okay, everything pretty well spread out except for that one over there, a little off the distance, but pretty close numbers, right? Does the number of dots on the dot plot tell you how many people were at the concert or how many students were in the math class? Well, let's go back and take a look at this in case you weren't sure. Let's read carefully. It was last night everyone at the school music concert wrote their age on a piece of paper and placed it in a box. Today, each of the students in the math class selected a random sample. So these dots represent what? Each of the students in a math class and their sample size. So every dot is the different sample size that a student in the math class drew. So you had a total here of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we had 25 students in the math class, and each of them drew 10 pieces of paper from the box in order to get a sample size. And that's what these dots are. So these dots, in terms of where they're located, are the sample mean age. But the dot is Sally's drawing, Nate's drawing, Michael's drawing, whatever it's going to be, whatever they drew. The mean age of the population was 35 years. Okay, so our mean age was 35 years. Got it. 35 years right there. If Elena picks a new sample size 10, sample of size 10 from this population, should she expect her sample to be within 1 year of the population mean? Okay, so the question is, if she, knowing the population mean is here at 35, would she expect to get something that's going to be 1 year away? Okay, will it fit in that box? Well, based upon what we see, I would say, well, what would you say? Hopefully you're looking at saying, are the odds that she's going to pick one inside that box? Probably not. You'd probably say no, not likely. It's possible, but when we look at this, we see that there are only, in this case here, only 9 out of the 25 are within 1 year of the population mean. Meaning there are a lot more that are outside that box. So if she did it, she might be outside, and that's okay. Now, what could Elena do to select a random sample that's more likely to have a sample mean within the 1 year? Well, if she wants to get closer, the best thing to do is to select a larger sample size. So instead of drawing just 10, move that up to drawing 20 or 30. The more times she does that, the more likely her sample is going to match the actual mean. Okay? Number 3. A random sample of people were asked which hand they prefer to write with. L, this is an L there, means they prefer to use their left hand. And R means they prefer to use their right hand. Based on this sample, estimate the proportion. Proportion, remember, is a fraction between 0 and 1, okay, of the population that prefers to write with their left hand. Well, let's see. We have 1, 2, out of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 2 out of 15. That is our proportion, our estimated proportion the population prefers with the left hand. As a decimal, if you chose to write that out, you could say 0.13. Again, that's between 0 and 1. If you wanted to look at percent-wise, you could also consider that as 13%. Hello, Eugene. All right. Andre would like to estimate the mean number of books for the students at his school read over summer break. He has a list of the names of all the students at the school, but he doesn't have time to ask every student how many books they read. What should Andre do to estimate the mean number of books? Okay, so he has a list of all the kids. There's a list, right? He has every kid's name listed in the whole school. Now, again, if you're at my school, that might be about 1,400 junior high students. That's a lot of people to ask, hey, how many books did you read? So what should he do? I would say he should use that list and create a sample. Maybe the sample size should be between 10 and 20, depending on your school size, to get a sample mean in order to answer his question. Okay? That would be the best thing to do there. I definitely would not ask 1,400 kids. That's a bit much. And finally, a hockey team has a 75% chance of winning against the opposing team in each game of the playoff series. To win the series, the team must be the first to win 4 games. Design a simulation for this event. Okay, so we want to make sure that whatever happens, they win 75% of the time. Now 75% is what? So 75% is like 75 out of 100 or 3 out of 4, which means I need to have a simulation where 3 times out of 4 I end up with a winning situation. Okay, now I could do I could put numbers in a hat, right? I could do like number tiles or number squares or cubes, and I could have I could make it so I have 1, 2, 3 of these dark ones and 1 white one, and whenever I get a dark one, that represents a win. Whenever I get the light one, I get a loss. And so I put those all in a bag and I just draw one out. And so for the first game, so if I do game 1, I look and see, what do I get? I draw one out, maybe I got a dark one. Okay. For game 2, maybe I draw one out and I got the light one. For game 3, I draw one out and I got a dark one. Game 4, okay, and I get another dark one. Okay, game 5, maybe I end up with a light one. And game 6, I end up with a dark one. Okay, so I don't know, you could practice simulation. So we could do that with some blocks. He could also, if you didn't want to do blocks, maybe you consider doing a spinner. If you do a spinner with 4 equal parts, okay, alright, you could either write a W on each one, and the win, win, win works like this, and the loss like that, or you could put numbers on them, right? You could number them 1, 2, 3, and 4, and then the numbers 1 to 3 equal wins, and then number 4 equals a loss, and you spin it until you see who wins. Okay? So what counts as a successful outcome in your simulation? If I used the block ones, I would say it's the dark block there. If I use a spinner, it might be the W if I put a W on it. Or if I put numbers on it, it would be the numbers 1 to 3. I'm giving you 3 different options here. Okay? Estimate the probability of using this simulation. Well, if I use this probability, if I use this simulation, it's going to be very, very high. The probability is a very high chance that it's going to win. I'm going to leave it like that for now. I think anything else is maybe a bit much for today. So the likelihood that the team's going to win is very, very great. The odds of them not winning is very, very small. So we can leave it at that because more likely they're going to get a win. Okay, that's it for today. Have a great day. See you next time.